Assalamualaikum, Doctor. Before we begin our presentation, let me briefly introduce our group members. We are Group 6 consisting of 5 members. Firstly, which is me, Nurul Wahida Afika, S81622. Second, Syed Shazwan, S78656. Third, Hamizah Husna, S79654. Fourth, Fion Hen Zuan Zuan, S80344. Fifth, Shiyu, S78659. In this question, the initial stock price is RM100. The stock can either move up or move down in one period. If the stock moves up, the price becomes RM100 multiple 1.20 equal RM120. The value 1.20 comes from the up factor U equal to 1.20. If the stock moves down, the price becomes RM100 multiple 0.85 equal RM85. The value 0.85 comes from the down factor D equals 0.85. The probability of an upward movement is given as P equals 0.6. So the probability of a downward movement is 1 minus 0.6 equals 0.4. Using this information, we need to calculate the expected lot return, the variance of the lot return, and the expected payoff and variance of a digital binary option. First, we calculate the logarithmic return. For the upward movement, the stock price changes from RM100 to RM120. Using the formula ln S1 per S0, we get ln 120 per 100, which is equal to 0.1823. For the downward movement, the stock price changes from RM100 to RM85. Using the same formula ln 85 per 100, which is ln 0.85, the answer is negative 0.1625. Next, we calculate the expected lot return. The formula is EY equal P ln U plus 1 minus P ln D. Substituting the values 0.6 multiple 0.1823 plus 0.5 multiple negative 0.1625 equal to 0.0444. Therefore, the expected lot return is 0.0444. Next, we calculate the variance. The formula for a binomial lot return is sigma 2y equal P 1 minus P ln U per D power of 2. Substituting the values 0.6 multiple 0.4 ln 1.20 per 0.85 power of 2. First, 1.20 divide 0.85 equal 1.4118. Then ln 1.4118 equals 0.3448. Squaring it gives 0.3448, the power of 2 equal to 0.1189. Finally, 0.6 multiple 0.4 multiple 0.1189. So the answer is 0.0285. Now we analyze the digital binary option. The option pays RM100 if the stock moves up and RM0 if it moves down. Since there are only two possible outcomes, this follows a Bernoulli distribution. The expected payoff is calculated using E payoff equal P multiple 100 plus 1 minus P multiple 0. Substituting the values 0.6 multiple 100 plus 0.4 multiple 0, so the equal is RM60. Next, we calculate the variance. The Bernoulli variance formula is sigma 2 payoff equal P1 minus P 100 minus 0 power of 2. Substituting the values 0.6 multiple 0.4 multiple 100 power of 2. So the answer is 2400.
For question 2, assume the logarithmic return of a market portfolio is driven by a Gaussian normal distribution with an expected annual return of m equal to 8% and a volatility standard deviation of sigma equal to 15%. Using the empirical properties of the Gaussian distribution, determine the approximate intervals within which 2 per 3, 67% and 95% of the portfolio's annual return outcomes will fall. By applying the empirical properties of the Gaussian distribution, we can determine the expected range of our returns. For approximately 67% of the outcomes, which represent one standard deviation from the mean, we calculate 8% plus minus 15%. This gives us an interval ranging from negative 7% to 23%. For 95% of the outcomes, representing two standard deviations, we double the volatility. The calculation becomes 8% plus minus 30%, resulting in a wider interval of negative 22% to 38%. For question part B, briefly discuss why assuming a perfect Gaussian world might underestimate risk during extreme market crashes like the 2008 financial crisis. Moving on to the risk critique, we must discuss why relying on the perfect Gaussian world is dangerous. The Gaussian or normal distribution assumes that extreme gains or losses occur very rarely. However, as we have seen during major financial crises, this assumption completely breaks down. Based on the market realities, we observe a few critical structural shifts. First, Financial returns often exhibit fat tails. This means that extreme losses occur much more frequently than a standard normal distribution would ever predict. Secondly, during a market crash, market volatility increases significantly, which violate the static parameter we usually input into Gaussian models. Finally, and perhaps most importantly, during a panic, asset prices tend to move together. When everything correlates and drops at the same time, it causes compounding, larger losses than expected. Therefore, a standard normal distribution will systematically underestimate the true tail risk of the market collapse.
So for the question 3, a high-frequency trading firm models the arrival of buy market orders using a Poisson distribution. The average arrival rate of buy orders is lambda equals to 4 orders per millisecond. The first one is state the expected value and the variance of order arrivals per millisecond for this asset. And the second one is calculate the exact probability that the firm receives exactly 2 buy orders in each millisecond. So for the first question, this question involves the Poisson distribution, which is used to model the number of events occurring within a fixed time interval. In finance, it's commonly used to model the arrival of buy and sell orders in the market. So for this question, the average arrival rate is lambda equals to 4 order per millisecond. One of the main properties of the Poisson distribution is that both of expected value and the variance are equal to lambda. Therefore, the expected value is 4, which means that on average, the trading firm is expected to receive 4 buy orders every millisecond. The variance is also 4, indicating that the variability of the order arrivals is equal to the average arrival rate. And for the second one, we calculate the probability that the trading firms receives exactly 2 buy orders in 1 millisecond. To do this, we use the Poisson probability formula where we substitute lambda equals to 4 and x equals to 2 into the equation. After performing the calculation, we obtain a probability of 0.1465 or approximately 14.65%.
My name is Lim Xiu and my number metric is S78659. So today I would like to talk about our dynamic Python tool built using NumPy and SkyPy.state to solve and verify our finance probability problems. For problem 1, the tools applies np.log to convert baseline factors into continuous log returns. From the question, we can know that our baseline, which is S0 is equals to 100, U is equals to 1.2, D is equals to 0.85, P is equals to 0.6, option up is equals to 100 and option down is equals to 0. These are our fixed baseline configurations variables for our problem 1. Weighted by our 60% probability, it outputs an expected lot return of 0.0444 and a dynamic option expected payoff of 60 ringgit. Moving to problem 2, we evaluate continuous risk. Notice that by interacting with our expected return variable right here, which are m is equals to 0.08 and sigma are equals to 0.15, the tools automatically maps out our empirical 67% and 95% risk intervals. The code implements states.norm.cdf to find the exact continuous area under the Gaussian curve, confirming a 78.26% coverage check. It matched to our manual distribution properties. Finally, for problem 3, we modeled high-frequency order arrivals. Since a Poisson distribution's mean and variance are structurally identical to its arrival rate, our tools set both to 4, and from the question we can know that our target X will be 2. Calling stats.poison.pmf, we will get the yields and exact probability of 14.65%. We have verified the correctness of our manual calculation by using Pythons. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh and a very good day. My name is Syed Shazwan bin Syed Nizam and my number metric is S78656. So now I'm going to demonstrate a financial probability calculator using a new values to prove that our scripts work dynamically under any conditions. But first, let's look into a few things first. First of all, as you can see here in our coding, there's a import numpy as np. Okay, so numpy stands for numerical Python and it is a gold standard library in data science for handling complex math. Other than that, we also have here import scipy stats as stats. Okay, so while numpy handles the algebra and basic calculus math, scipy provides the heavy statistical distributions. Okay, next we are going to start our demonstration. Okay, as shown before is the new values that I'll be using in our coding. Okay, so let's start. Okay, as you can see here, the compiler asks us to input the value for upward multiplier, which is variable as u. So we'll put it 1.3, and then the downward multiplier 0.75, and then the probability p 0.7, and the payoff if up, which is 100, and payoff if down 0. Next, the compiler asks us to enter an expected annual return up, which is m. The value is 0.1, and for the volatility, which is sigma, the value is 0.2. Okay, next we will be entering the average order arrival rate, which is the lambda, and our value is 5.5, and the target order count X is 3. So here is shown the calculated outputs of our task. Okay, next I'll be showing the manual calculation to proving that our coding works. First, we'll be finding the expected logarithmic return, which is EY. To get EY, we have to find the ln of U, which is ln of 1.3, that equals to 0.2624, and then the ln of D, which is ln 0.75, equal to negative 0.2677. To get EY, we have to use the formula of P times ln U plus 1 minus P times ln D. P, as we know, is the probability, which is 0.7. So here we will get 0.7 times 0.2624 plus 1 minus 0.7 times negative 0.2677. Okay, here, after calculating this formula, we will get the answer, which is 0.0974, or equal to 9.74%. Okay, next we have to find the variance of the log return, which is sigma square y. The formula is P times 1 minus P times ln U minus ln D square. So here as state, 0.7 times 0.3 times 0.2624 minus negative 0.2877 square, that we will get 0.21 times 0.55 square. Okay, here we will get the answer of 0.0635. Okay, to get the expected option payoff, we have to sum up the payoff of up and payoff of down, which is 0.7 times 100 for payoff up and 0.3 times 0 for payoff down. Then together the sum is RM 70 ringgit. Okay, to find the variance of the option payoff, which is sigma square payoff, the formula is P times 1 minus P times 2 times the payoff up minus payoff down square, which is we will get 0.7 times 0.3 in bracket 100 square. That will get the answer of 2100. And then to find the microstructure asset pricing problem, as we know, the EX is equal to lambda, which is 5.5, and also the var X equal to lambda, which is also 5.5. Using the Poisson probability mass function, we get the formula which is Px equal to x is equal to exponent to the power of negative lambda times lambda to the power of x over the factorial of x. So we get the value is exponent to the power of negative 5.5 times 5.5 to the power of 3 over the factorial of 3, and we will get the answer which is 0.